Okay, so let's begin our this week. So this is week 5. We are going to cover about continue to talk about autoregressive models. First of all, we'll talk about the PixelRNN and PixelCNN, and then we'll talk about transformers, and also we're going to mention that some modern usage of the autoregressive model combining with diffusion models. We'll talk a little bit about it, like the broad parts about the diffusion model is a spatial autoregression and the block diffusion, which use diffusion models on generated text data. But before that, let's talk about the homework. So this is our homework, which should be already posted on E3. This is our homework 2。好，所以我们先讲一下第二次的作业。那第二次作业的话呢，就是用so the homework 2 is to use homework 2 is to use character level text generation text to familiar with the n-gram models and some neural network related to autoregressive models like LSTM or GRU, or if you are wishing to use transformers, that would be also fine to use that. But in this homework, I'm more expected to you guys to use the like LSTM or GRU RNN models。好，所以这次作业主要是用来熟悉一下 autoregressive model 在语言和文字上的，特别是 n-gram 和那个比如说用神经网络像是 GRU、LSTM、transformer 也可以，但是你甚至用 CNN 也可以因为你用 n-gram 用 CNN 也可以，但就都可以不过 you can even use one-dimensional convolutional neural networks. However, there's some reference notebooks that using LSTM. So it might be easier if you just using the RNN. But anyway, any model, any neural network model is perfect for this homework. So first of all, you need to collect your data set so that you can train your simple model. So you can either use like English text, Chinese text, or code like Linux code, or any large enough code base on GitHub and collect them. Then you need to train the data. The data should contain at least 5,000 sentences or comparable amount of data. Otherwise, it would be just too little data to do significant training, so that you can. So if because our goal is to let you familiar with or get a feeling of what the autoregressive can do and what is the limitation of the context window, which is covered in the part we talk about the n-gram. So in n-gram, the context window is related to the n itself. Okay, so you need proper data set in order to get enough statistics. So I would suggest that you get a data set that containing at least 5,000 sentences. However, if you are not, if you collect some data that training data that is not, does not have enough training data, I have no way to tell the differences. So it's just a suggestion. The hard requirement is in both cases. 好，所以这边建议你有一个 data set 有5000个句子但是假如说你某种原因就是不愿意，就是没有弄到5000个句子，其实因为我们交作业的方式 ，so because our method of submit a homework is to E3, so if you didn't follow the list, if collect training data that is containing like 4,000 sentences. We have no way to tell differences. So the hard requirement 所以你要是只用一个4000个句子，其实我们这也分不出来了。只是说这边是建议，对啊，就会比较好一点点。So the first part is to try to mimic the character level models that we talked about in last week. So you gather the statistics like this one, like the N gram. First you gather and you have to do for 2 different N. Like you can do like a 5 gram or like a 10 gram. Depends on you are using English or using Chinese training data. So the code, you can actually use the code, modify the code that provided in the notebook that we mentioned last week. Okay, store the information in a counter. So this is also a suggestion because this is not in a bold case. And you can, but in the notebook you submit, you have to show how many distinct tuples are in the training data. So when we call, that is how many keys are in a dictionary, and which tuple appears most time in the data set. 好，所以这边有出题字就是比较硬的一个需求。第一个就是这边只是强迫你从这个你统计下来资料里头，你真的去看这个，理解一下这个资料是什么。它重点就是理解这个资料。那只是因为我常常讲说，你要去看懂这个东西，或理解这个东西，同学可能不是很确定我在讲什么，什么叫做理解它，什么叫懂它那其中一个，这边的所谓 B 跟 C 这边就是帮助你去理解它和懂它，因为你这东西就是懂得就懂，你理解它就是理解它了嘛，你那个时候就会知道了。你还会问这个问题，表示你还有一些东西不理解。那，所以这边的话就来辅助你，让你知道说什么叫做理解，因为有的时候我们就会问一些问题，然后知道它的答案。比方说，你统计下来的东西，你跑完了嘛？特别是我们的程式码也是别人那边，你可能就用别人写好的东西，你做一些修改，那跑完了就跑完了。可是跑完的东西，就算是别人写的程式码，也可以变成你的东西啊。你统计下来的东西还是你的，你可以从里头得到一些资讯。好，那其中一些比较基础的资讯是，里头你至少可以回答，我这边跑完这个资料集头，我是 n gram 嘛，有多少不同的前面的 n-1有多少不同的种类，至少可以回答这个问题啊。这个东西是懂的一步，就是说你要去理解它的那个资讯的一部分。Okay, so one way to understand what the data is okay, so you will have a lot of questions about this data, and you have a way to access the answer, to obtain the answer from the data you have collected. So one information that is probably quite apparent, interesting, is that how many distinct tuples are in the dictionary that you collected. So that's one question. And another one is, okay, which kind of prefix tuples, like this one, is the most common one in the data set? Or which are the top 10? And there are other questions like, okay, how many tuples that just appears once? And how many tuples appears kind of little times, like less than 10 times? There are tons of different questions you can ask about this collected data. So if you have tons of different questions and you are interested in this collected data, and you have a way to access the answer, then I will consider that you are familiar with this data. You can get information with this data. So this homework helps you to get started with this approach. Okay, so also the D is showing the top 3 candidates of XT that is most likely to appear right after above tuple. When I say above tuple is the most common one here. Because this is, when we collect this thing, this is a and the value is a counter. So you can use the counter to find the most common 3 candidates that can be the next character. Okay, so that's another way to familiar with the data you collected. Then finally, our goal is to generate something similar to the text. So generate 3 paragraphs of text according to the statistics. You may start from any tuples that appeared in the dataset. Basically, just try to generate 3 different paragraphs of text. And you may want to generate 3 different paragraphs. So you have to start from some point. Because the setting of these like ungrained models, you have to start with something that already existed in the paragraph. So just pick a small tuple in the dictionary you collected, start from there, then to run a paragraph. That's all about this, the second part of the homework. 好，所以基本上就是这几个需求了。然后那就是前面当然是一些 B, C, D are some basic requirements so that you can familiar with the data you collected. And E is the goal, that is to generate the 3 paragraph. In part 2, you have to do all the B, C, D, E with at least 2 different N. So if you are really interested in the data and try to get a feeling, you probably will want to try more N, like a lot of different N. You don't have to show all the. I mean, if you try like 10 different N, you don't have to show all your work, because there will be a lot of different paragraphs. I mean, for me, I tried this like several hours to investigate the different kind of text to familiar with the property of this text, so that I can get a feeling of what the data can do, what the information is contained in this data. So I probably cannot show all the work in one notebook because I don't have just one data set. I have a lot of different data sets. But in the homework, you only need to submit for one data set for 2 different, and that is enough to show something. 好，所以作业里头，其实你真正在做，如果你对这个东西产生一些感觉，真的要产生一些感觉，其实要试好几个不同的 data set， 很多不同的 N 啊。那这边只是有点算是强迫你试2个不同的 N， 然后暗示你说这边是多于一个 N， 哦，只是这样子而已。好，那再来的话是 ，OK, so after this one, this one you can use the notebook that we discussed in last week, and also there's another another notebook that is about the RNN. Pretty much you do the same thing, except that you don't have many different N. You just have your. I mean, this is not an ungrained model. This is a LSTM model or a GRU model. So you use your neural network model. Presumably, you are using an. If you have in DOP, you don't know which one to use. You can use GRU because this is more suitable for this homework. I personally like using one-dimensional CNN because it is much faster. But still, I would suggest using GRU. If you prefer like LSTM, that is fine. But GRU is a little bit easier to training in my experience. Okay, so instead of using counter, you train neural network to learn the conditional probability. And the only hard requirement is to generate 3 paragraphs of text using the neural network model. That's all. There are some things you can try to do a similar thing like BCD. mostly for like the D part. You can use D part. You can compare with this result in when you correct encounter. You can compare the statistical trend from the neural network and the result that you collect. The statistics you actually collected. You can compare with them. That is kind of interesting. But for the homework itself, you only need to generate 3 paragraphs of text using any kind of neural network models that to predict the next character. Okay, so that's all about the homework. So let's begin with the autoregressive model, starting with PixelCNN. My plan for this week is we are going to, after the PixelCNN and PixelRNN, we're going to talk about about the transformers model and a little bit about language model. Continue to talk about a little bit about language model. We already get started last week because the N-gram model is a simplified, like an autoregressive model, autoregressive language model. Although it seems pretty simple, they share a lot of similarity to the most trending model, like GPT model or Llama models. So please do not underestimate or overlook those models. Although they seem to be very, very simple, they serve a foundation of understanding what the large language model, current large language models like GPT does. By comparing the modern model and the simple model like LCM model and like the statistic model, simple statistic model, you will be appreciate what the capability or what the transformers can do. And you will have a motivation or like a reason to understand why they wish to design the transformers model. And if the GRU model, LCM model, or maybe like the simple statistic model that we do, is if they are perfectly fine, then transformer model won't be necessary to be invented. So there must be some reason people want to invent transformer model. And actually, there are many different models using attention, like combining LSTM and attention together to work with like language text like translations or maybe like text generations even before the transformers was introduced. People sometimes feel that okay, attention pretty much bind to the transformer model, but in fact before the transformers there has already people already know what the attention is. There's already a thing called attention, and LSTM. There are certain language model that combine the attention model with like LSTM or GRU, and they are actually doing language tests. But you may know that you may realize that the transformers is the current winners for all the models, so it must have some spatial characteristics or certain strengths that people are using it. 好，所以你从前面比较简单的模型，你其实可以知道的事情是，它其实跟现在的那个 transformer 的模型都很像，但是它更简单。所以你可以了解两个关系，也可以了解说，其中一个就是知道为什么 transformer 会被发明。事实上 ，attention 在更早就已经有在用，而且用在语言模型上面，而且不但用在语言模型上面，但是它用的是在比如说跟 LCM 结合啊， 跟那个什么 GRU 那些结合。所以为什么 transformer 会用？它其实有它的特点，它一定是解决了某个问题。所以你知道那些简单的模型是什么，你才可以知道说为什么要有 transformer，然后它是一个很简单的模型，但是它解决了什么问题，而且它为什么它的优点在什么地方，它强的地方在什么地方。Okay, but before that, let's review how to apply the autoregressive model to generate image. Before we talk about, we'll talk about transformer later, but let's focus on first on LTM, and later on we'll talk about how to use the CNN in similar way. So there are different papers that is related to this topic. The first one is pixel recurrent neural networks. This paper actually introduced both PixelRNN and PixelCNN. Although the name suggests it is just about the PixelRNN, but in this paper, the PixelCNN is also introduced. However, the most popular PixelCNN architecture is in fact introduced in this paper later. It's a follow-up paper for this pixel recurrent neural network. Although the title suggests it is focusing on conditional image generation, but I think the most important part of this paper is the introduction of the gated CNN, because in my experience and a lot of people suggest it is actually very powerful tools if you wish to use CNN on autoregressive way or maybe in general. Also, that is a very useful, powerful building block that is people even use today. Okay, so these are the two papers related to these topics. And this is also in an implementation that you can see for the TensorFlow, but people are using PyTorch a lot recently, so you can also refer to some PyTorch implementation of the like PixelCNN and PixelRNN. Okay, so this one is illustration of how the PixelRNN is supposed to work. It is also an autoregressive model, but it works on pixel. The one obvious issues about this approach is, okay, if we wish to generate a sequence, the sequence is, in mathematical terminology, it is totally ordered because we can generate one by one. It has an apparent order. 所以如果我们把 CNN、RN 这种东西用应该说 RN 的 autoregressive model 用在比如说一个数列啊，或者一个文字上面，它有一个很明显的一个顺序，第一个字、第二个字、第三个字。你当然可以有一些比较神奇的顺序啦，135792680，你可以用任何顺序，但是很明显它有一个明显的顺序嘛，第一个字、第二个字、第三个字、第四个字。So in a more like a linear sequence data, it has an obvious or apparent order of the elements. However, for an image, because it is a two-dimensional, there is no natural or satisfying order for the pixels. Of course, you can have certain certain arbitrary orders, like from left to right, from top to bottom. Yes, you can have certain that kind of order, but it doesn't feel that naturally. At least there are several different choices that may be considered to be equally natural. So the first, when you read the title like pixel by pixel generation or pixel, when you see the pixel, you probably already guess that, okay, it is using auto-regressive models, but it wish to generate the pixel one by one. So the first question is, okay, which order does this paper choose? It in fact choose different, a few different type of orders on the pixels. 好，所以看到这个，你一定想说，第一个问题就是，好，它是怎么是把那个我们知道 ，OK，它一定是可能是用 auto-regressive model，然后一个点一个点升嘛，没问题。但是它的点所谓的 pixel， 它怎么排？哪一个是第一个 pixel， 哪个第二 pixel？ So in this picture, it pretty much suggests, okay, it is some kind of top down. The order is some kind of top down. In the computer image, because our image is stored in the memory, in the computer memory. The computer memory is a linear address. So if we follow that address, the order should be from top to down, from top to bottom, from left to right. Okay, so it more like this one is x1, x2, x3, x4. So first from left to right. So you start from the first row from left to right, then you go from the second row from left to right, then you go from the third row from left to right, and so on. So this is one order, one kind of order. The benefit of this kind of order is your image is already probably stored in this order. So there are certain some issues. The first issue is that, okay, if we are considering a color image, it is in fact has 3 different color like RGB for each pixel. So do we need to consider different color channel one by one, like or maybe we consider the RGB together. So that's one issue. And some other issue is if we choose this kind of order like x1, x2, x3, x4 to xn, then xn plus 1 is in fact very far away from xn. So in fact, xn is kind of like one of the rightmost pixel, and xn plus 1 is sort of like the leftmost pixel. So this order may seems to be a little bit kind of unrelated because they are so far away. So imagine if you are using an n-gram model, then this n-gram model perhaps may not be very effective because this pixel may be totally unrelated to these 3 pixels or these 5 these 5 pixels because they are far away. One is on the left side and the others on the right side. So if we are using the n-gram model, it probably will not very effective, will not come with very good result. So a better order might be just a suggestion. It might be something like x1 to xn, and this one get to the xn plus 1, and n plus 2, n plus 3, and so on, like this one. But this still lacks some thing that we probably need is because, okay, we know that, say, this pixel is probably also related to the pixel that is right above it. But if while using this kind of order, although every pixels next to each other is in fact geometrically or spatially they are actually next to each other, but we are not using all the information. Okay, so I'm just let you get some feeling of why the orders is a issue and why does this problem when we apply to the image, this is something we need to consider about and what are they worried about. In fact, you can see that in this paper, they use different ways to do the order, although it is still kind of from top to down and mostly from left to right, but still from the following, you will see that why they are kind of worried about or they are concerned about this issue. This is because this is a nature question or things we need to consider about arise from this approach. When I say this approach, I mean by applying a autoregressive model on image. 好，所以首先就是你要知道为什么顺序这件事情很重要，是因为我刚才举的例子主要是，如果我们直接是 x1 到 xn， 然后 xn 加1到 xn 加xn 加3这样下去，这个当然好处是它跟记忆体我们现在的影像在记忆体直接放进去的顺序是一致的，但问题是 xn 到 xn 加1，你可以发现它突然跳到很远的地方，从右边跳到左边。那比方说你从之前 n-gram 的模型那边去想，你就发现 n-gram 模型可能会失效，因为这3个点，比如说我们用 4gram 嘛，所以用这3个点去预测这个，但他们很可能完全无关，因为图片可能很大，所以这个时候这个方法可能就会失效了，除非你的那个 n-gram 的 n 超级大了，那可能还有点帮助，但是如果你只用这3个 n-gram， 就是 4gram， 然后用这3个去预测下一个，很可能这个模型跟它本质上就无法训练。好，所以这也是为什么你要先了解 n-gram 模型，可以帮助你去想象，你有个更简单的东西去帮助你去想象你的所谓 autoregressive model 可能做的事情。那你就算是用 GRU 或者 LTM， 那当然原则上来说，它这边会全部记下来，可是有点远嘛。他真的有办法记住，刚好这个是他看过 x1 啊，你在做 xn 加1的时候，他看过 x1 没有错，但是他真的可以记得这个 x1 是它上面的这个点吗？这实在是还蛮困难的事情，除非你有一些周期性的忘记啊，就是他走 n 步之后，他就记起来前 n 步的事情哦，这个事情就它的顺序有点怪。那一种可能性，你说，哎，那我可不可以这样子到 n， 然后变 n 加1，然后 n 加2 n 加3，但好一点了。至少没有刚才的问题，但是它会少利用到一些资讯哦，这是另外一层的问题，就是我们会担心少用到资讯，因为这个东西虽然被前面这2个影响到，但是上面这个点跟它也很有关系啊。那如果我们没有它的资讯，他们会不会就图片就破裂的很严重？这边应该是红色的，这边可能是蓝色，这边就可能应该是这2个颜色综合色比较可能了。但是这边不知道上面的资讯，它这上面就会开始裂开了。哦，所以顺序很重要的原因在这边，你可以知道为什么接下来会用到等下的方法。Okay, so the most important thing is the order. Because autoregressive models is you can consider autoregressive model as that okay, we are using we need to have an order of generation. I mean, in an autoregressive way, what we are doing is to generate a certain element first, and after we generate certain elements, we generate the next element and the next element and the next element. So we probably want to have for each, like this one, we wish it to have a context. The context meaning the condition. I mean, in this formula, or like the condition probability. So when we say context, we mean that the condition for the conditional probability. For this xi, the context is the things before it. So in the linear order sequential data, this context is pretty obvious or apparent. There's apparent to select the context, but in the image, the most important thing is to identify the dependency, or like in this terminology, the context. So like, okay, if we wish to generate this one, of course, we cannot use the future things to do that, but we can, what we want to do is, okay, can we use all the things before it to generate this guy, especially the things around it, the neighbor, the pixel in the neighborhood of this xi. So there might be a multi-scale context. So one way to do that is you might want to generate to consider context in multi-scale. That is one way to do that. Okay, so we can generate a lower resolution things first, like this one. Then we generate. So this is another way to consider order. That we first generate a lower resolution one, and after we generate a lower resolution one, then we can generate other pixels to refine the generation. Also, there are different ways to do that. But anyway, it is a good way to consider it in the sense of context. So one way to do that is to do a multi-scale context. And the other consideration is like this one is, okay, how do we handle the coloring? The coloring, like for each pixel, there are RGB. Do we need to consider the RGB separately, or like to consider them one by one? Okay, the choice of the pixel CNN and PixelRNN is that first of all, they're considering each channel or each element is discrete. Okay, so keeping in mind, we are considering a discrete scenario, just like what we do for like the character-based models. Each element is, we only have finite many different possible element. Like in the character-based model, each potential element is only a letter, an English letter, or like a space or a number, but they have just a finite set of them. So we'll talk about that later, but the thing is, this makes sense that we are considering RGB to be separated element. So because each of the R has like 256 possible value of intensity, and also green has 256 possible in intensity, and so is for the blue channel. So if we consider them together, so there are two choices. We can consider RGB together, or we have to consider them separately. If we consider them together, then if we are still using the discrete approach, then we'll have like 256 times 256 times 256 possible kind of situations. So that is the size of the token. That is too huge. You can consider, instead of just have like a 26 alphabet, we have 10 million alphabets. That will make things very difficult to do the statistics. You will have a huge data set in order to make some sense. So that's why this choice is kind of apparent. If we choose to have using a discrete autoregression, not the the discrete autoregression model, not the like continuous autoregression model, like the linear autoregressive model like this one. If we are not using this one, we're not using a continuous space, then it only makes sense to separate each channel, so that we only will need 256 different like tokens, or like kind of elements。所以其中一个要决定就是 RGB 要不要切开来，还是要合在一起。然后，但是因为我们使用的是离散的空间，也就是说，等一下会说一下，就是它其实有选择了。但是你当然一开始做实验可能会直接用黑白的，就避免掉这个问题，用灰阶的先避免掉这个问题。但是现在的话，就他后面会说他已经决定用离散，那你决定用离散之后，你的 RGB 就几乎必须要切开了，因为如果不切开的话 ，RGB 看成一个个体的话，256乘256乘256那个东西太大了，那就那个东西不好做，所以几乎就一定要切开了。Okay, so because we separate the RGB, I mean each one considered as a individual element. So they will have an order. So the order is quite simple. That the first is R, the second is G, and the third is B. So we'll have an order of RGB. When we do in PixelCNN, we were using a mask to ensure the order. So if each element will not see any element that is not in the context, or if you trying to fill the element in like in the past or in the future, that is we are using a mask to avoid that each element to see the future, so that the generation will be when we're training the things, it will not see the future, so we can actually apply it to generate things. 所以这个 mask A 和 mask B 先不用太担心它了，因为这是等一下 PixelCNN 要用到的。那这个 mask 在之后像 GPT 那些训练的时候也会用到。但这边这个图只是要说 ，so this is only give you a graph so that you can illustration that you can see that actually we need to consider RGB different channel. So for even in each pixel, the different channel RGB, you need to give it an order. This order is arbitrary, but you have to have an order. So because we usually say like RGB, so the order is the first is R and the second is G and the third is B. So anyway, in here we will have an order. So later on, we are not going to talk about the color channel, but you have I mean it is pretty straightforward to apply because we already have an order of the different color channel. 好，所以之后这边只是先告诉你说这个 RGB 我们有考虑到了，那就是照它的顺序。那之后就比较不会讲到这件事，因为它会让这个整个解释太复杂。Okay, but as here you can see explicitly you can express these things by using a conditional probability. Like okay, the R channel is only generated consider context that okay the previous pixels and the green is using the all previous pixels and the R channel for the same pixel. And for the blue, you can use all the previous pixels and both R and G channels. Okay, so let's talk about the pixel as discrete variable. This is also an interesting choice. So as I probably already mentioned, when you read a paper or read the research results, one efficient way to do that or help you to understand the sense is to view it as a problem of choice. When you see a title or after reading the abstract, you already have an idea or possible way to solve this problem. The only thing matter is which route or which path is chosen by the author of this paper. So that will make you find things that is mostly interesting or make you easier to understand your choice. 好，所以这也是我之前讲过，就是你在读文章或什么时候，其实最容易的读法，或者应该做的东西，就是你先知道哪边有选择，然后这个选择有哪几种，大概有哪几种选择，那这几个选择就可以帮助你去记忆，或者是你去看到这个作者他选的是什么，那你就知道，你可以把它整个记下来，就好像你在点菜一样，可能什么前菜是什么啊，主菜有几个选择，然后什么饮料啊、点心啊，大概知道有哪几个选项，然后你这样看下来就，比如说有人点餐的时候，你就可以知道他是点什么搭配什么，然后大概想一下他为什么他因为点这个主菜，他因为不吃牛肉，所以他不会点牛肉，所以他点的是什么？那因为点了牛肉，他就配什么饮料，有点像这种感觉，这样就比较容易记。你要是完全从头读到尾，你只是一个字一个字去记的话，那个菜单就很难记。哦，甚至说你不晓得，他会不会点了2个主菜啊或什么？但是他菜单可能选下来就是那几个选项。对，先看到你从标题和它的比如说摘要，你看完之后，先大概知道说它有什么选项。比方说我们前面 Pixel CNN 或 Pixel RN，你大概就知道 OK，第一个它应该有几个困难点，它要选的东西是顺序，然后 RGB 那个东西是它的困难点，它要选。好，还有一个东西就是因为我们比如说你特别是你知道那个 N-gram model 的时候，你知道其实这个 auto-equation model 它在那个 discrete 的情况，在离散的情况，它还蛮有效的，至少可以用 N-gram 类似 N-gram 方式去处理，然后也可以用 LCM 的方式去处理，它还蛮有效的。虽然它也可以做连续的，像是传统的就是标准的那种 linear 的 autoregressive 那种东西，然后你 LCM 其实也可以用连续的，但这边是一个选项，就是它要用连续和离散，因为有这种选项，有这个选择。Also, you can identify there is a choice right here, whether or not to use discrete variables. Sometimes because the uh, the author may not explicitly point out this is a choice because they just choose that. But still you should identify there is a potential choice right here, and you will see that okay the author already chose this option. But in this case, in fact, um, by using pixel as a discrete variable is in fact sort of unpopular choice or sort of incorrect choice. So it actually in this paper explain why they choose pixel as discrete variable. The reason that it is unpopular or like a incorrect choice is because the general rule for choosing uh, the value to be discrete or like continuous is depends on like we have already covered. The general rule is whether it has an order. Also, like what we talk about MNIST, although the target is like a 0, 1, 2, 3, 4, 5, but each category, there's no actually like 1 is more close to 2, or 1 is not uh, close to like 7. There's no such thing because 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 are all just label. Although 2 consider when we consider as a number, 2 is more close to 1. But arguably, like 7 looks more like 1 actually. So there's no reason that the 2 should be more close to 1. So if you are using the 0, 1, 2, 3, 4, 5 as a continuous value, then it makes no sense. Because when you consider it as a continuous value, the 2 will be close to 1, and the 7 is not close to 1. But that is not our intention, so that is not a correct. So instead, we're using 1/2 encoding to encode the label. That is simply because they are just no relationship to each other. They are just some kind of symbols or category names. Of course, 1, 2, 3, 4, 5, they have some certain arithmetics or mathematical interpretations, but we do in the MNIST to do the digital digits, handwritten digits recognitions. We're not trying to do like additions, multiplications, subtractions. We're not trying to do that. We're just doing the recognitions. So there's nothing we need to use a continuous variable. So we use discrete variable. But we use some to predict something like the price of some product, or like the how long the time this object were going to survive, things like that. We'll consider them as continuous variables, because it provides more structure to correlate it to these things, because we know that when we do the prediction, if the correct answer is like 10, and we predict something like 9.9, it is better than we predict something like 5 or 200, even though 9.9 is not equal to 10. Same as 5 is not equal to 10. I mean, correct answer is 10. So if we predict something like 9.9, or 5, or 200, no matter what we predict, it is incorrect. But if we are trying to predict something like the survival time, or like the price, you would be more pleased if we are predict something like 9 or 9.9 instead of predict something like 5 or 200. So if it is this case, it is more natural. In a general rule, it's more natural to use a continuous variable. Comparing to the MNIST scenario, if the correct answer is like 5, no matter your prediction is 6 or 4, or maybe like 9 or 1, they are equally incorrect. There's nothing like, okay, if the correct answer is 5, but if you predict like 6, okay, I give you like a partially correct, partially points. There's nothing like that. In MNIST, it doesn't matter that 6 and 5 are just their consequent numbers. Also, that's the key differences. 好，所以标准的看法就是你只要看它预测，就是它的有没有连续性啊。比如说，就是刚才说了，就是如果你要预测一个价格，那正确答案是10，但是你预测是9.9，你会觉得够好了。即使9.9不等于10，或者预测正确答案是9的时候，正确答案是10，你预测9的时候，总是比你预测5或者是15要好很多。如果是这样的话，它就是连续的。但是像 MNIST 的正确答案是5的时候，你就算预测是6或4，也不会让你加分嘛。所以这个是很明显的。But when we consider about the trying to consider pixels, the intensity of pixels, of course, what I mean is for each channel, but it is easier to say pixel than say channel. Even the name says that it's a pixel CNN or pixel RN, not saying the pixel channel CNN. Okay, so when I say pixel, when you do actually apply it to the color images, it probably apply to each channel. But I'm going to say the pixel. So for the intensity of each pixel, from 0 to 255, if the correct value should be like 200, and if your prediction is 199, 199, or 201, that would be pretty good, because our naked eye cannot tell the difference between these little differences of the intensity. So in these rules, when we do the predict the intensity of pixel, it should be like continuous variable. Of course, if you are using like the VQ GAN things, the after the encoder, we already get a discrete token space. Then that is totally fine to use pixel CNN. But currently, we're not talking about the FQ gain. We are still working on the pixel original pixel space. Although, like we mentioned before, in the FQ gain, eventually they are using the pixel CNN, pixel RN to generate the latent distribution, which in that case, specifically in that case, they won't have this issue. But in general, I mean, in the original paper of pixel CNN and the pixel RN, they are dealing with the raw images. So this is an interesting choice. So the general rules is to use continuous variables. However, that is just a general rule. Sometimes we have to consider different aspect from a thing. By using a discrete variable, it is in fact like what in the aspect of what we just mentioned. It does not using the structure of the target because they have some continuity. So the loss function, if you are using not considering the ordering itself, it may be considered as a weakness, or like at least it does not take the benefit. That's for sure. But when we consider a thing, there are many different aspects need to be considered. By using the discrete token, there are certain benefit. One of the benefit it is because it is easier to handling. Just kind of like what we do for like the n-gram thing. So if you have that experience, you can understand why using the discrete things would be have some simplicity and benefits. So actually there are previous approach to use autorecursive models on image generation. Although they may have different choice of like the orders or other things, but most of them are using continuous distribution. That's understandable because that is a more natural, or it actually follow the general rule of choosing the whether or using a discrete or continuous variable. But in Pixel CNN and Pixel RN, they are choosing a different way. OK， 就是在这前面我们其实有讲过那几个用 autoregressive model 生的图形的那几个例子嘛。对，那其实你就知道有很多，其实就是 Pixel RN、Pixel 之间不是第一个用 autoregressive 去生图形的东西，只是这个东西比较成功的。那前面的东西可能比较虎啊那些的，好，那这个东西比较成功的。Okay, so the PixelRNN CNN, so one of the key contribution or observation is over the PixelRNN CNN is that, okay, when we use discrete variables, although it against the general rule, but the general rule is not a hard rule. It's just it is not a hard rule. It is not a no go to forbidden you using it. It's just saying, okay, it's a more benefit to using the continuous space instead of discrete space if your target is a continuous distribution. Okay, so the PixelRNN and Pixel CNN is against this general rule, but it gets a better result. So each channel variables is simply take one of the 256 discrete values. There's absolutely no consideration about the topological structure of the pixel intensity. When I say the topological structure, it means like, okay, 200 is more close to 199 than 100 or 0. That is what I mean by the topological probability, characteristic or structure. So in the whole PixelRNN, PixelCN, they consider these variables are totally discrete variables. They're using all the things like cross entropies to use as a loss function and absolutely consider nothing about the topological structure of this value. But it actually experimentally it actually get better result. It probably because it is easier to learn because LSTM is very difficult to train. That is one of the purpose of the homework that we were given. Because you can see that the discrete variable, by comparing to the simple statistic method, if you are trying to use the GRU or STM, you find it not that easy to actually get the training done. Although theoretically, they will have a long-term memory and a short-term memory, and it will consider indefinitely long context. In fact, the context can be an infinitely long sequence. So in principle, it break the limitation of an n-gram thing. But in general, it would be very difficult to train. Sometimes it may perform even worse than the simple model if you are not training it correctly. Okay, so there's always a consideration about how to train the model, because there are always some potential difficulty when training model, even though everything is seemingly better, like the continuous distribution things. Even though in some aspect it seemingly no downside, but it is more difficult to train. So you may not actually get the benefit of the things that you are expected to get from the continuous distribution. So sometimes easier to train is the most important, is the key benefit of everything. So in this case, it is a typical case or example of easier to train or able to actually train the model is the most important factor among all other considerations. 好，所以这边其实是一个很有趣的例子是，虽然说连续的变数看起来好像比较好，但是离散的这个比较好训练嘛。这个其实是这个大概可以弄，但是重要的是这个地方刚好显示出来了，好训练的这个特质其实凌驾于，有的时候是很多时候是凌驾于其他的东西上面，其他考量上面，包含说刚才说的连续性的那个范围的考量那些的。So one particular example that maybe you may encounter a lot is like sometimes we are trying to considering a continuous variable problem that has too many different choices. And that is a new problem that you are trying to study or to solve. I think one of the first step, a good or first step is to discretize the problem. Like suppose you have difficulty to analyze the value. So for one example, the score of for one examination score for like the whole in a school for students. So every student has a different score, like from 0 to 100. There are a lot of different scores. So one way to do that is to consider some categories. Like we have 10 different categories of scores, like from 0 to 10, 10 to 20, 20 to 30, or 30 to 40, and so on. And finally, you get a 90 to 100. So you only have 10 categories. And you can do some statistic to see, okay, how many students have a score in the first category, which is from 0 to 10, and how many are in the second, and how many are in the last category. And you can say, okay, we see a trend. The most students are in the middle, perhaps most students are in the range of 50 to 60. You can actually find some conclusion. 好，所以其中一个例子是说，比如说你要考虑说一个班上所有学生的成绩，可能从0到100分嘛，看起来乱七八糟，也很难去分析。那一个简单第一步可能做的事情就是把它离散化。当然0到100本来就是离散的啦，但是我的意思是说，你可以想象它可能都是连续的成绩，比如说0，你可能说那个成绩刚好就是一个实数里头的一个数字，你可以这样想。好，那一个简单做法就是，好不好？我先把它分成0到10分，10到20，20到30，30到40，分成10个等级。这时候你就可以看到统计出来它有一个趋势啊，或者是说哪个东西最多。最多的就50%的学生，他是在50到60分中间。几乎没有学生是在0到10分中间，你就可以很快去分析了。So this discretization method can make the similarly difficult issues to be more simple. We can simplify it to an easier question, like to determine a student whether it's pass or fail. We like give a okay, if you are 60, you get a score like 60 or above, then you are pass. And if you are less than 60, and your score is less than 60, you fail. So we can have a ratio of how many students are pass and how many students are fail. This is also sort of a simplify the issue. Although it may be arguably like, okay, the student which get the score like 61 is not much better than the student who get the score like 59. However, we tend to simplify the problem, even though it actually sacrifices something might be worth to consider. 所以我们其实我们常常就会把问题把它先简化，然后虽然它中间会牺牲一些，但是它会好处理。有很多连续的东西，你去把它离散化之后，就包含像积分也是一样，我们都会把它离散化，只不过那个它的分的会很细啦。但常常你把很多问题把它先离散化之后，让它变成少数几个类别，事情就会好做很多会好做很多。就像我们把成绩给 A、B、C、D 这种分数，其实也是在做类似的事情把分成等地 A、B、C、D， 让它好处理很多时候都是在做这件事情。Okay, so this is an interesting choice to use the discrete variable, which is also a key characteristic of a PixelCNN and PixelRNN. Okay, so let's now focus on the order of the pixels. So the first one way to do that is quite interesting, is that PixelRNN, one variation of the PixelRNN is to use raw LSTM. There's also another by LSTM variation, diagonal by LSTM variation, but so there's PixelCNN variation. But what we are trying to say here is, let's see the first one. This is not the only one way, but this is one interesting way. So we are trying, one way to do that is, okay, can we just consider it row by row? 好，所以一个方法就是我们如果把一个 row 这样来看的时候 ，if we consider it row by row, then it becomes a sequence. The first row, the second row, the third row. So if our RNN works on this way, on the raw, then it seems that okay, we can reduce it to the regular, um, LSTM problem, right? Okay, so we row by row from top to bottom. Although arguably it should call it a raw RNN, not PixelRNN. But anyway, so we can compute the feature of the whole row at once. And so how do we actually compute the row one by one? Can we use just the original STM? In fact, we can do that. But if we simply do the whole row by row, then it certainly cannot have a name called PixelCNN or PixelRN because then actually no consideration over each pixel. It's just LSTM applied to the image row by row. The input vector is a factor. I mean, the input of everything xn is a factor, so there's absolutely no problem. Which you can just use the original LSTM and consider the first row as an input vector x1 and the second row as x2 and x3 and x4. You can actually do that. But in raw LSTM of the PixelRNN, it actually consider a more detail about things, about the images. It actually uses the convolution, one-dimensional convolution, instead of a general linear layer in the LSTM. 好，所以它其实额外做了一件事情，去考虑它影像的特性，那就是它使用了 convolution， 它在 LSTM 里头使用了 convolution 1D。那这边的话，因为 this is because the I mean, when we dealing with images, it is very popular to use convolution to handling the image data, because convolution naturally consider the spatial uniformness, and smart spatial correlation things about the image. 因为 convolution 它天生就第一个，因为 convolution 它 kernel 会移动嘛，所以它第一个就考虑过它的空间上的一致性，第二个就因为它的 kernel 只有在它附近的点附近去处理嘛，所以它有考虑到每一个点跟它附近的点比较相关这两件事情，所以 convolution 很常用。那这边没有用完整的 convolution 2D， 它把其中一个 dimension 用 LCM 来处理，另外一个 dimension 用 convolution 来处理。So in the approach of raw LSTM, it still uses convolution for one of the dimension, and for the other dimension, it uses LSTM. So kind of like a mixture of the LTM and the convolution. So the actual implementation is to replace the linear layer in the LTM to convolution 1D layer. Okay, so the actual formula, so this is the LCM formula, like the get, for get, hidden, it is, let me check. Okay, there's a forget get, output get, import get, and the hidden, and see context get, forget get, input get. It uses the context get, forget, cell state and the hidden state. Yes, like what we do. The context get is okay. The get for the input. So I mean context get and input get. Okay. So it is exactly the formula that we talk about for the LCM. You can see that the context is forget something and update something, and when the output sends, it take from the output instead of okay. This is a get output get, and using the hyperbolic tangent to on the context. There's probably only one thing that is different is on the output get, because the output get should be depends on the new new context like CI in our last illustration of the LTM. But anyway, you can see the things right here. The only difference is that you can see instead of using a linear layer, it has a kernel KSSS and using convolution right here. So the only difference is here. It is not a linear layer. It is a convolution. So this is a convolution of the hidden layer and X and put them together. Alternatively, you can consider it as two channels, like HI-1 and XI are two channels, and we're using this kernel, using one convolution kernel apply on the concatenant of HI-1 and XI。所以这边基本上就是我们上次讲的 LCM， 唯一的差别就只有这边这个地方，在做 get 的时候，这边用的是 convolution， 而不是用的是 linear。那其他因为都是逐项相乘，它就跟那个什么 linear 那没关系，它就把所有 linear 换成 convolution， 就这样子而已。Okay, so that's one way to do the PixelRNN. I mean PixelRNN, sorry, PixelRNN. It's quite interesting, but the issue is that okay, there are several different issues. One issue is we probably need to generate the first row. If we want to generate the image unconditionally, we will probably have some way to generate the first row, and it may not be the most easy problem that we can generate. Unlike to generate the first pixel, that should be easy because we only have like 256 possible situations. We can simply do a statistic to generate the first pixel. But to generate the first row, that's another problem. Perhaps we can have another model to generate the first row, and because this is just a simple sequence, we probably can use the LCM directly, but that is an issue. 好，所以第一个问题就是说，如果你要用这个东西来生图的话，如果是 unconditioned 生图的话，你要先能够生出第一个 row。那第一个 row 并不是那么好生啊，虽然你可能说哦，这个东西如果变成第一个 row 的时候，它就是一个 sequence 嘛，那就变成原本的 LCM 就好了，也是可以的。那如果像后来其他几个模型，它只要生第一个 pixel， 那倒是很容易，因为第一个 pixel 你只要统计就行了，统计完之后，它只有256种情况嘛，所以你就算不统计也没有太大的差别了，反正统计完之后随便一个起始值，那就可以剩下了。但现在这个东西你必须要先生一个 row， 那这个 row 就像刚才说，你可能要其他方法去生。The second issue, is that it is not exactly issue, but it's a consideration that why we come to deal with the first access and the second access in a different way. Since we are using have to choose an order, so there will be a chance that we deal the first access and second access in a slightly different way. That is acceptable, but in the case of raw LTM, we actually consider the first this x axis. We're using the probability of convolution, and for the y-axis we're using the LSTM. So that is so different. Also, that is consideration because we're not using the property that x and y axis are kind of symmetric, sort of symmetric. We're not using this property. So that's another consideration. So this is by far, although it has several benefits, like the elegancy of kind of split the problem into two parts, and each part has a sort of elegant solutions, but it is by far not the most satisfying solution. Okay, so another way to do that is to consider a bidirectional LTM, and we actually just do the LTM. The context or dependency is sort of like this one. So for each row, we do the bidirectional. We actually do the bidirectional LTM, and we are going from up to down, row by row. We're still going row by row, but for each one of them, do the bidirectional LTM. There's one easy thing because of the dependency of the pixels. What we actually want is something like this one. Each pixel is depends on the previous pixels, like the upper one and the left one. And for this one, it depends on these two. And because this one is depends on this one and this one. So in order to make it more elegant and more kind of efficient, we feel this is our goal, our final goal to do that. This is our final goal to have this kind of dependency, like a context. We're trying to use diagonal by LCM as our tool to implement this intuition. 好，所以这是我们理想中的一个 dependency， 就是每一个点它就是根据它上方或左方的的点做个 dependency。当然，因为你要生这两个点嘛，所以这三个点也要生出来。那当然，更前面的点都要先生出来。So if we wish to generate this pixel, then we have to generate these two pixels first, and then generate. Of course, before we generate these two pixels, we have to generate these three pixels first, and these two pixels, and of course, the first pixel is this one. So this is our goal. If you look at this image, it is not directly that it can use for diagonal by LSTM, because if we simply generate like row by row, it will be similar. I mean, this one should be generated later on, or like this one. What we have to generate before this pixel is all the lighter ones. So this one should not depend on this guy and this guy. So not because this guy is on the in the upper row, if we generate row by row using by LSTM directly, this is not what we intended. This is not a dependency that we intend to have. So we actually do a simple trick to kind of square the images a little bit. What we do is something like this one. We square the second row to shift it to 1 pixel right, and shift the third row 2 pixel right, and shift the pixel 3 pixel right. So you can see that for each column, it has the same kind of same importance, or like the same priority, because they have the same shade of the color, which indicate the priority of these things. So if we just do this square and the shifting, every column, if we generate it column by column, then there will be no dependency problem, because these all kind of things are dependent on the previous column. So we can actually generate it column by column. So that's why we can actually use the by LSTM column by column without have the risk of like seeing the future, or when we say seeing the future is something like is generate. We're using the information of the pixel when training. We're using a pixel information of a pixel that is not already generated. So by shifting it like this one, and we're doing it column by column, each column, it is safe to generate. It's safe to assume that when we generate each pixel in the same column, every column on the left side hand side has already been generated. Has already been generated. So we are free to actually access to the information of them. 好，所以我们做这种就只是每一个 row 把它往右移一个，往右移一个，往右移一个。只要这样做之后，因为我们的目标是左边这个啊，但是我们把它往右移一个之后呢，它刚好每一个 column 每一个行它的顺序呢，就跟它的生成的顺序会有关的。它可以确保说我要升前面的行，我要升这边这个 pixel 的时候，它前面每一行，其实我都已经可以确保它已经都被生出来了。好，所以我们就照这个顺序去升的时候，因为我们每一个行，我们升的顺序可以这一行升完，再升这一行，再升这一行，再升这一行，可以完全都是一行一行升，所以我们可以用 BioSTM 每一行每一行的去把它生出来，你不用担心说哦看到不应该看到资讯。好，如果你用 row by row 像这样子 row by row 或者这边 column by column 的话，它比如说你在升这个点的时候看到这个点，或者升这个点的时候可能看到这个点。哦，那这些东西是你或这个点啊还没有被生出来。你在训练的时候，你训练的时候，你就是把那张图给它去训练嘛，所以你可以看到所有的这张图上面资料集的所有点。可是我们想象的是说，我们生的时候是一个一个这样生出来的，所以你会看到，当你真的在用的时候，它不该是会生出来的点。哦，所以我们就没办法用白那个 LSTM。但是如果你现在这样做的话，你就可以用双方向的 LSTM，哦，完全可以这样做。Okay, so it is actually kind of like a convolution. Although it is done by using a BioSTM, and because when we do the training, the dependency is on the left-hand side, we can safely assume that everything on the left-hand side is already generated when we do the inference. So in fact, we can do the training on every pixel at once, parallelly. We can do the things parallelly. So from left to right, column by column, to do that, and using a convolution kernel size of 2 by 1 to do that. Also, in this implementation, it's also using a residual connection. Because residual connection is sort of popular and kind of standard right now. So I think this is just a mention of the choice, although it has a special mention on they are using the residual connection, but because residual connection is so popular and so standard, I think when we read it today, it just okay. It also use the residual connection. That's it. 好，所以因为它这边也有用到 residual connection， 但是就 residual connection 已经很标准嘛，那你就这边就是 OK， 我读到，它可以选择要和不要嘛。大家通常是要，然后它也是要 ，OK， 就这样。比较意外的是，跟这个前面也就是选项没有错了，但是比较意外的是用 discrete， 这是它用 discrete， 这是比较特别的。那这边有很多选项，就是它的顺序，它选项一大堆，那这当然也要，那它就用其中几种，所以这边也是要特别注意的。那这个倒是就 OK， 他用了就正常，没什么啊，没什么不好啊，就是他用了而已。Okay, so about the PixelRNN, the LSTM when we do the training, the LTM is still need to do it more like sequentially because the architecture of the LSTM. But when we, if you see that right here, it mostly kind of like what we are doing is similar to convolution, very similar to convolution because every pixel is dependent on certain neighbors that is preceding to it. The only thing we need to consider is the order. The convolution thing is, especially if you have already seen the squealed the image, like the shifting of each row by different size, it kind of hint that, okay, we can probably using a convolution instead of the LSTM. If we're doing a multiple layer of convolution, it may have enough relation. I mean, each pixel may get enough the information from the previous context. This is because if we're using an LSTM, it will get all the context because LSTM is supposed to have a long-term memory. It can remember the context, at least theoretically. But for the for convolution, for one layer of convolution, it only kind of like an n-gram. It only access a fixed length of a context. But with higher layer or larger kernel of convolution, it can access the information to a far further distance, but it still has a fixed distance of context. But in practice, because convolution has already been very successful, so it may not be a huge issue. The only thing that we need to be very careful about is to allow the pixel to do not see the feature. But because of the this kind of things, we may be using something like a skew image, or like using a proper mask to prevent the pixel to see the feature information. Okay, so here, but the idea is pretty much the same. The only difference is that the pixel CN does not has a long range memory. It just has used the convolution to transmit or passing the information from further away pixels. 所以如果我们放弃那个长期记忆的话，就不要让它照顺序。那个 pixel CN 其实就做差不多的事情嘛，只是说它没有长期性的记忆，然后但它可以训练的时候超快的，因为它可以完全一次训练完。那这个东西你就因为你要用它的记忆嘛，所以就它要照记忆去做。所以它的 dependency 可以看到这个点，它就跟前面的东西有关。那这个点它就跟前面的顺序，然后以及跟它哪个东西是有关的。Okay, so this is what you can find in the pixel CNN graph, like this one. However, you can see that the title of the paper, the first paper, is still PixelRNN. That is PixelRNN still get better result. So in the next paper, like the second one, it actually consider why the PixelRNN is better. Is that long-term memory really matter, or is there anything else to separate the PixelRNN and the PixelCNN? It turns out that the metric maybe appears in the exists in the get layers. Okay, so because experience on the convolution neural networks, and we know that the convolution is probably pretty good to understand the image already. So it might not be the perspective, the field of the, or like the long-term memory that the LSTM have. So what else separate the RNN and like the traditional, the standard convolution? One thing that in LSTM, which is very unique or like interesting, is the gated things. You can see that the in the formula of the LSTM, no matter the convolution, LSTM like raw LSTM or like the original LSTM, there has a lot of different gate, like the forget gate, output gate, input gate, a lot of different gate, and they use something like element-wise multiplication to the gate to do things. So maybe this is maybe this is what magic happens. So inspired by the LCM architecture, a thing called the gated convolution layer is introduced. So similarly, kind of like a raw LSTM, but it is using for the convolution layer. It has doing two separate convolution. One is to just the usual convolution with a hyperbolic tangent activation function. So this one is the original one. But instead of using it directly, it also has a gated convolution. So it is a simple convolution with a gate. 好，所以到底为什么 LSTM 比较厉害 ？Pixel CNN 跟 Pixel RNN 比，为什么 Pixel RNN 比较厉害？可能有很多不同的原因嘛，它们中间有很多差异性。长期记忆可能不是那么重要的事情，因为今天本来就可以看到你好几层叠在一起，就看得够远了。所以那会不会其他地方？那这边就是实验，就也许就是因为 gate 的关系，因为 LTM 我们刚刚看到有一大堆 gate， 那所以他就把 gate 的东西加到 convolution 里头了，它主要算是用到这个像这个东西，前面的东西就是正常的 convolution 啊，这只是它的 nonlinear， 但是我们乘上一个 gate。好 ，so after this modification, the Pixel CNN get pretty good performance and pretty good result, and also get a very good, still got a very good like a parallel training benefits. So that's why I think Pixel CNN is getting more popular comparing to Pixel RNN. Pixel CNN is more popular and faster. Here is I think here's a result of the first Pixel. So by using Pixel CNN or Pixel RNN, not the first, the raw LSTM, by using the second Pixel CNN, Pixel RNN and the Pixel CNN, you can see that we still need to generate the first pixel. And here is the kind of like the statistic of the channels of first pixels. Kind of like this one. And here is some sample result of the images generated by the Pixel CNN and the PixelRNN applying to the CFR10 dataset. Okay, so that's is the Pixel CNN and the PixelRNN, and I think the take-home message is that when we have a tool like auto-regression models, and when we want to apply it to different kind of scenarios, there will be a lot of different options. Maybe some of the options are not quite common, like the discrete vs continuous distribution. So sometimes you need to try something not against the general convention or general wisdom. Sometimes that is a key point. and consider all the different options, like consider ordering. It is a thing that is to try different kind of possible options if you are not sure, because there will be a lot of different options. And finally, when we find something is better than the other, try to figure out which ingredient makes the difference. Like the case, the PixelRNN find out, okay, maybe the gated things is a key. Although we probably doesn't know why this works, or we're not sure why this works, but if we identify this ingredient and apply to another things, we can see what happens, and maybe we can find something else, new findings. 所以这边重要的就是，我觉得这个很有趣的一个例子，可以让你看到，第一个就是你就是看到不同的选项嘛，然后它选项有一种可能性就是 OK， 你常见还不常见的，有的时候不要太快把选项就锁死，就是两个都可以试一下，然后你会发现一个大家都认为可以走正常的选项，也许不见得比一个偏门的选项要更好。再来就是也许你会有很多选项，那不确定哪一个，那也就多试一下。那两个共同点就是多试一下，就是不要放弃选项，然后你要看到那些选项。那最后一个是 Pixel 跟 CNN Pixel 啊，你发现两个选项 ，A 选项比 B 选项好，你可以尝试去从 A 选项里头找出它的成分，哪一个部分是让它比 B 选项更好的，因为它中间可能很多不一样的地方，尝试去把它孤立出来。那就像 PixelRNN 比 PixelCNN 好，你不要太早就觉得因为 PixelRNN LTM 有长期记忆，它一定比较好，就这样结束，那你就错过那个 gated 这样可能更好。去详细看它里头内容，然后试试看。虽然我们也不太确定为什么 gated 更好，但是它就是让我们发现这东西是一个有效的成分。那这东西后来也用在很多不同的地方上面，这个有点像是那个医学或者药学可能发现了一个东西，可能是治疗那个心脏病的，但是可以用在其他地方。一开始可能是这个东西这个食物看起来有治疗效果，然后把中间成分独立出来，变成有药，然后后来又发现这个药可以用在其他地方，也很有效，然后做了一些修改。那这 gated 的这个部分到现在的the gated things are quite useful tools for as a building block for the neural network. So even in the modern language models, we're still using the gated things in the MLP part. Also, that is quite useful thing. Okay, so here are some examples of other things. But first of all, we are trying to see two examples that autoregressive models can be used. Like what we see that although intuitively the autoregressive model should use on linear order sequential data, but as you can see that with some modification, we can apply it to a two-dimensional data as well. So here are more examples, and mostly related to the diffusion models. So first of all is that observation that diffusion model is in fact an autoregressive model. If you consider the spectral autoregression, spectral space, like a frequency domain. It also has a Colab notebook that you can play with. So this is a blog post for investigating the image that is in the spectral domain, and to see that, okay, in fact, when we observe the spectral domain, the progress of the things is pretty much looks, when we do the diffusion model, it actually looks kind of like autoregressive model, and it also apply to the generation of audios, because audios is also pretty straightforward to use to fill it in a spatial domain. So that's observation that is related to diffusion models, which we use, which is one of the major method that we use to generate image and videos and other things. And another interesting thing is the block diffusion models that is recently used to generate to be labeled as diffusion language model. It actually kind of like the name suggests, it is use both the diffusion models and auto-aggressive model together in order to generate text. So one of the the example to illustrate the sense is here. This one. If we use the auto regression directly, it is high quality, like a GPT things. Although we haven't introduced the transformer yet, it is high quality, arbitrary length, and it has a key value catching. But it doesn't, kind of like LSTM, it doesn't have the benefit of to parallelize generation. If we're using a diffusion model directly to generate text, then there are several different attempts to use diffusion to generate language model, but none of them are as successful as what the like the GPT-based model. So it is lower quality, and the diffusion model tends to have the fixed length. This is the limitation. And also, one of the interesting thing is the KV cache about the language model. So it can using attention to kind of gradually increasing the length, but you can still using the attention efficiently. But the benefit is that diffusion model can do it to parallelize, can generate things parallelizedly. So by using a block diffusion, like basically you have several blocks, each block is a diffusion model, then it can have the both benefit of both method. So that is a kind of like applying autoregressive principle. That's just not the applying, like using the autoregressive work with the diffusion model. Okay, so that's to mention of the some of the studies. Okay, in the last hour, final hour of these lectures, we are going to introduce the transformers so that we can talk about first the transformers on the text models, and on the image generation. Mostly this is for image generation. Secondly, we will have going to talk about large language model next week. So in order to talk about the current modern large language model, we have to talk about transformers and the GPT. So we'll talk about transformer here so that you can understand what it is. Okay, so let's see this one. Here are some examples of using the GPT kind of model or transformer kind of model to do the generation. So one thing is to using GPT directly, kind of like a PixelRNN, but using the GPT directly on the image data. Also, it is called image GPT. And another interesting is a timing transformer for high resolution image synthesis. It can be considered as a predecessor of the stable diffusion. It can generate pretty good result. Like all of these results, the architecture can be considered as a successor of the Pico VAE because this is the paper is called the FIQ game, called the FIQ game. It is sort of like the FIQ VAE, but instead of using pixel CNN as to generate a distribution, it used the transformer. The benefit of using a transformer is it can naturally work with text condition. So it is still a log autoregressive model, but because you know that the transformer can work pretty good with the text input. So we have a prefix that has a prefix that is a text tokens, and here concat it with the image tokens. Then use a transformer to generate the following token of the pixels, and then using a decoder to like a FIQ VA decoder to decode the things back to the image. Okay, so that is what the FIQ GAN is. So the important thing he see here is how the text condition is going to affect the transformer. I mean, affect the image generation. In a modern diffusion model, things are similar. We have the stable diffusion like architecture. We have a VAE encoder and the decoder. But when we generate the things, we're not using a transformer directly. We're using a diffusion model like a UNet right here. So the text is used. We're using a different way to guide the diffusion model by the text prompt. But the elegancy of this FIQ GAN approach is that it is so natural that to use a text prompt to guide the image generation, because they are just a sequence, so we can do it pretty much without any modification. So this one is actually the first generation of the text prompt based image generation. 好，所以 FIQ GAN 其实是第一代真的有人开始做那个文字声影像的部分。This is the first generation of text to image generation, and back then there has already a community of artists or like amateur artists or maybe professional. I'm not sure, but there's a community of people trying to explore the possibility of using FIQ GAN to generate images, like the prompt engineering. There are already a healthy amount of research on the text prompt engineering back then, but not as huge as today because it already like everyone has certain experience on text to image generation right now. But back then, even it is just cannot compare to today. But I think back then there is also a healthy community that people are using these kind of tools to generate new things. 好，所以其实这个很早前就有人在做，就是文字声，那个时候很早就有人在做这一类的东西，那个还蛮有趣的啦。不过那时候是比较小众的，然后现在就多了啊。那个时候像这种 condition 声的啊，文字声的啊，其实都有了，就是你看起来也挺不错的，其实看起来也挺不错的啊。只是说就现在的东西当然比较厉害了，因为技术在进步。啊，不过这个东西是已经好久了，那也是那个时候就可以看到，只是没有猜到那么快啦，就是说会爆炸到大家都在用这件事情。好， Okay, so let's go back to talk about what the transformer is. One way to see it is to use Wikipedia, because transformer is so popular, it's so standard. Like we said, there are different ways to investigating a topic. One way is to use Wikipedia. If the topic is so popular and so standard, then Wikipedia is a good start. This applies to the transformer because although it is not so not considered as an old technology, the transformer is invented like in 2017. So it is not something that developed like decades ago. But because it is so popular and so trendy, I think Wikipedia is still serving as a pretty good starting point. But on the other hand, um, there are other ways to study things, like lecture notes and the textbook is also a good way to start. The transformer is interesting. Is on some topics it is more suitable if you study the paper directly. If it is a recent result, if it is something like invented like 20 or 30 years ago, I won't suggest you to read the original paper, like the original LCM paper. The original LCM is okay. It's good paper. It is a good. Of course, it's a good paper. But the style of the writing of the writing style of the paper is kind of ancient. So a lot of terminologies change, and a lot of tests of the like the conventions are changed. So it is not recommended that you read the original paper of the LTM as a starting point. So instead, you can read a tutorial from the textbook or like lecture notes. But transformer is an interesting thing, although it is relatively new. So the paper is really good. It is still suitable for reading. Currently, it's still very good for reading. But Wikipedia is also very good, and there are textbooks for transformers that is worth reading, and there are lecture notes and tutorials. So any resource is suitable for learning transformer, or not just one. Most of the topic there are certain things, certain format of the materials that is more suitable for them, like textbook or like lecture note and Wikipedia, like we introduced before. Depends on how mature, how advanced that is. But for transformer, currently every source is available. Also, you can either start from Wikipedia or you can start from the original paper. We are going to start from original paper because this paper is so cited and because it is so still accessible and readable. So I suggest you can still read it at least once. I'm not going all through the paper, but I'm going to several key points that you can easily understand the architecture. And finally, we probably will have a code with it. We'll talk about code later. So let's begin with what is the architecture of it. You start with this graph. You will see this illustration in many of the articles or books that discuss the transformers, because this is the graph that describe what the transformer is. Let me get a stylus that I can write things on it. So it consists two parts. One is the encoder. Okay, so the stylus not working. Oh, okay. It seems my age has 就是我的浏览器好像有问题，它当掉的感觉。这地方本来它应该可以上面画图的。我今天直接先讲。Okay, so left part is the encoder, and the right part is the decoder. For the architecture, transformer architecture, it will have n decoder block, n encoder block, and n decoder block together. Okay. When we talk about the language model, probably we'll cover the sequential to sequential model a little bit, probably not. Probably briefly about that. But this is a successor of the sequential to sequential model. The idea of a transformer is a successor of a sequential to sequential model. Okay. 好。Let me do it again. Okay, so this guy is the encoder. Oh, okay, so when I write on it, I'm not sure why, but it is hanging. 我现在没办法画它，每次一画它就整个当掉，所以我只能用说的。Okay, so 不知道是录影还是什么，应该不知道为什么会发生这种事情。从来没有发生过这种事情。好吧，那我们就不要画了，因为它看起来会有点问题。我也没有开太多东西啊。好。Okay, so let's see. There will be n blocks, depends on how large your model is. So when you invest in like the llama or something, you will see that okay, it will have. 好吧，那我们等一下好了，有点耐心好了，这个其实有点糟糕，这样让我没办法讲。不要啊，好，为什么会这样？所以我只要看那个图就好了。那我看其他地方，因为我其他地方可能也有那个图。不晓得为什么会这样子。好，那我这边就不要画了，但是就本来是想说用画的会比较容易看清楚是什么部分了。好。So there will be when you see like the GPT, maybe not GPT 3, GPT 4, but GPT 2, or for like Llama model or like QA model, we'll see okay, it has how many blocks. That is correlated to these guys. So there were two similar parts. One is the encoder, and the other is a decoder for the transformer. But for the modern models like GPT, it only has a decoder, and it will not have a multi-head cross attention. Since just to remind you that the GPT is even simpler than transformer, but the full transformer has two parts. One is encoder, and the other is a decoder. The models like BERT, you're using only the encoder, and like the T5, it has encoder and decoder part. Encoder and decoder are sort of similar because they are getting some input in here. One thing you can keep in mind is that originally this kind of language model are designed for like translation. So if you want to imagine one example, one task, then you are imagine something like a translation. Or the translation is like consider like from English to Chinese translation. So the encoder is actually reading. We run the encoder first on the English text on each layer. You will have on each you have a lot of different blocks, and it run on the sentence. So the input are kind of corresponded to the English text, and the output is something that is generated, like translated things. So the encoder scans for the English text, and then it will start to generate the Chinese translated text. So that's why here is an input, but it called the output, because you can see that this is the first thing, like a start at the beginning. It will like the start of a sentence, and after it getting the input from the encoder, it will generate the first character that is translated, and when taking this output, the first output here as the input, it will generate the next character and so on. And for each of the generating process, it will take information that is extracted from the encoder. 好，所以你可以想象这是一个翻译任务哦，最典型的东西翻译任务，当然它可以用在其他地方了，就像是那个 auto regression，也可以用在很多地方。但是我们先用一个例子来看，你会比较具体。哦，是翻译任务，就是像英文翻成中文。哦，所以这个地方它encoder 可以自己先跑，它跑在英文上面。哦，这个地方可以完全先跑。你可以看到它这边的箭头，它不需要 decoder， 这边它完全可以独立都跑完。等一下你可以看到这个this error is one thing that you can observe from the error is the dependency. So you can see that the encoder is not dependent on anything of the output. So you can run the encoder directly, separately on the input of the source. 所以然后这边的话就是一般的那个 auto regressive 的地方，所以就是如果你只跑 decoder 的话，就很像 auto regressive 的地方。所以好，不是这边是翻译成中文嘛？最开始可能是句子的开始一个特别的 token， 然后开始就一个中文字这样翻译过去，每翻一个字就变成这边的 input。所以这边虽然是 decoder 的 input， 但它叫 output 哦，可是它其实是 input 啊。当然翻译过程中，它可以从 encoder 这边前面已经跑完了 encoder 这边拿它的资讯过来。好，那 GPT 因为它没有 encoder 嘛，这块就省略掉了，只是这样子。Okay, so let's first see the encoder first, because encoder is not depends on the decoder, so we can run it independently. So let's first see what happens to the encoder. So every time we have a sequence of things, of sequence of elements, kind of like what we do for LSTM. So for each of the token we have an input embedding. So because we are considering as a translation things, so the input things is in a discrete space, like we have a vocabulary like 1,000, 10,000 vocabularies. So each vocabulary is a discrete label or discrete item. We will first want to translate each thing kind of like one hot, but you don't need to actually have one hot because typically there are thousands of vocabulary. So typically there are just one number to indicate the index that's a vocabulary in the dictionary. So we will have a sequence like 35, 43, 125, 2, 75. This is kind of like a numerical sequence, and each sequence, each number is an index that's corresponding to a token. You can consider the token is a word, but not a word because it is a spatial dictionary designed for the. It is still a dictionary, but the words is not entirely like an English word in an English dictionary. It's kind of like a part of the word. So it is something like a subword things. 好，所以它的输入其实就是一堆数字，那每个数字对应到其实就是，如果你在翻译里头对应到就是每个英文字的一个 token 啊，但它总之它就是一堆数字。So before we feed these numbers into any kind of neural networks, and because they are discrete, so we cannot just use the value as is, because kind of like what we discussed for the discrete or continuous things, they are discrete. So we need to treat them as a discrete things. But still, we need to convert everything into a vector. So what we do is we don't know what it is, which number will be which vector. So we construct a dictionary. We call the input embedding. Input embedding is just a huge dictionary that, okay, suppose we have 1,000 vocabulary. Then this embedding keep a record of 1,000 vector corresponded to each of the vocabulary. So if the first input is an input like index 3, we check this array or dictionary to find the third like a vector. And this is our first vector. And if the second one is 35, then we find the corresponding vector and put into the second place. So the input is a sequence of number. And after we have the input embedding, we will have a sequence of vectors. And this embedding is trainable. So at the beginning, it is just randomly initialized. And after the training process, it will have like you're using the ADAM, like a back propagation, and using like ADAMW or other method, it will be trained to a specific value. So it is trainable. But the purpose of this guy is translating a sequence of number to a sequence of vectors. Okay, this sequence of vectors it's pretty okay, but as you will see that after this block, for this block, we will not going to have any positional information about each vector. As we will see in the attention mechanism, it will not containing, okay, of course, if we put the vector in a sequence, like the first one, second one, third one, we know that the first one is this guy, and the second one is this guy. But because how the transformer blocks works, it will ignore the order of the things it is given. So, in another word, if you shuffle the things, the vector, it will have an equivalent output as well. It will equivalent output as well. Of course, the output is going to shuffle, but the output of this encoder, for each, if you shuffle it back, it will have exactly the same output because it will ignore the position altogether. So in order to, because when we do the translation, the grammar is important. The grammar depends on the position. So we will have to inject. So one way to solve the issue is to inject the positional information into the vector itself. So the number, okay, this vector is the first one. This vector is the second one. We have to put this information on itself. It's kind of like if you have a lot of different shoes in a class, people have the same shoes or same backpack, same kind of style backpack, and we want to put them to collect together. And the order may be like shuffled or mashed up. So how do we get the correct? So after the class finished, people want to retrieve their own items, how can we make sure each guy retrieve their own items? There's one thing, simple thing. The first guy write its name or its like the position number on the items that it's going to be put in here in the box or in the storage. So you just write your name or your number on it. So after, even though when we put the things into your shoes into a box or in a storage, they're going to mix up. When you retrieve your item, you just see, okay, my number is 74, so I'm going to here to pick up my order, my shoes of that which is numbered at 74. So that's it. 好，所以因为那个 transformer 本身，因为它机制的关系，它不会在意它的那个编号嘛，所以这边的话，我们很单纯就是在每一个你等于说你的 factor 进去之后，它根本就是把它打乱了，它去处理的，有点像这样子了。虽然最后输出的时候，它会依照它的编号去做输出，但是它不知道前面每一个东西的位置，它没有那个资讯在里头，所以我们很简单，就是把它执行下去，就很像说你现在每一个人有一颗一模一样的球，你丢到一个，就是你可能不能带进去里头嘛，你要先放在一个收藏，然后出来之后拿出来，要怎么确保你的东西可以拿到你自己的东西？如果它的那个收藏的东西就是一个袋子，很容易就被打乱了，你就写上你的名字嘛，或写上你的号码。这边也是一样，我们就写上它的号码。So how do we do the things that which is analogy to writing your name on or writing the position on? This is called the positional encoding. There are several different ways to do a positional encoding. So one way is predefined things like sine cosine things. You can see that, and sometimes you can do a learnable, trainable position, kind of like the input embedding. So for now, you can see this, consider this as a trainable embedding. There are also some more advanced one like a rope or rotational based embedding way to do that. But for the original one, they are considered two type of embedding. One is the trainable, and the other one is the sine cosine thing. But anyway, this is also kind of like an input embedding. For each index, but this index are not corresponding to the vocabulary, are corresponding to the position. For each index, we can find an embedding factor. And this embedding factor has exactly the same dimension of the input embedding. So the position encoding and the input embedding has the same dimension. And they are simply add together, like a factor addition together. 当你拿到位置的资讯跟那个每一个那个 factor 在中间那个一堆 embedding factor， 你就把那个位置资讯跟那个 factor 直接加在一起。所以有没有 wonder why not just concatenate them? It seems to be more natural because, okay, position and the semantic main meaning of each token are definitely separate, should be in separate space. So why should we mix them up? It makes more sense to just concatenate them, right? It is certainly doable. The idea is actually used in something like rope encoding, or maybe like in, I think in DeepSeek V2. DeepSeek V2 also use similar separating things to compress things. And of course, you can just use concatenate instead of addition. And so you will have a lot of different freedom. But it is a convention that the standard way to do that is using addition. And it seems that there's no differences. And it's a more popular way to use addition instead of using concatenate. 所以你可以想说，那个位置资讯为什么不直接把它 concate 跟它 concate， 而是用相加的？就这是惯例啦，就是其实实际上跑起来没有差太多，然后这个惯例就是这样做。那当然它有它的优点，所以在 DeepSeek 的时候 P2 应该有用到某种把它分离的方式，让它比较更容易。然后像 rope 的概念，某种情况你可以把它视为它是分离的。但是实际上来说，这边两边它其实就 rope 那边跟那个更复杂一点点啦，其实更复杂。它的也不完全是这样做，但重点就是你直接把它 concate 其实也可以啦，你可以，只是大部分程式码或者在用的话，它都是加在一起。所以这边的话标准就是加在一起，它没有差太多。Okay, so we got our input. So we are not covering the transformer block yet. We are simply talking about the input. How do we input to encoding the input? So after we get the input, we are going to use a thing called the multi-head attention that we are going to introduce a little bit later. In general, in previous lectures, we introduced the attention first, then we introduce this graph. But I think you probably already have some idea, at least some popular science idea of what attention is. Attention is something that you find the relation of each token to or each factors to other. Let me just say tokens. For each token, how related this token to another token? That is the thing, and you use this kind of information to generate your output. So one of the key components is multi-head attention. Although technically we haven't introduced it yet, but you can consider it is an important block right here. And the output is also a sequence of tokens. It is also a sequence of tokens. I mean, a sequence of vectors. It will have the same dimension as the input, so we can add right here as a residual in a sense of like a residual block. So they must have the same dimension. And there's a normalization layer. Normalization is a popular building block of the mother networks to ensure the convergence and the trainability. If you without a normalization layer, usually it is difficult to train. Although recently there is a publish about the dynamic hyperbolic tangents to replace the normalized layer, so that we can have a similar performance of the transformer like architecture without the normalizing layer, because normalizing layer also usually has some people usually have certain consideration, especially about the batch normalization. But usually the normalization here is a layer normalization. There will be certain variation about it, but usually there was normalization layer right here. In this original transformer, it used a layer normalization, and after the normal this guy, it will get a feed-forward network. And this feed-forward network is actually applied element-wise. That is, this multi-head attention is applied on a whole sequence altogether. But the feed-forward, you may wonder, okay, if we have a feed-forward, why do we even need a multi-head attention? The key answer is this feed-forward is not a feed-forward on the whole sequence. It is a feed-forward on each of the vector. So it can be considered as a generalized nonlinear layer. But this is just simple feed-forward network instead of just one activation. Because it works on each of a vector. So it can be considered as a projector or encoder or things. It also has add and norm as pretty much a similar reason before. Like the add is because of the residual architecture, and the norm is a normalization things. they are just popular design to make sure that this network is trainable, is easily trainable. So that is the encoder. So the input is a sequence, and the output is also a sequence. And in each of the blocks, we will have a sequence of output that has the same dimension. That is the characteristic of these transformer things. It is a sequence to sequence architecture. So finally we'll have output. There are several reasons that this feedword is only applied to the element wise. The one reason is that if we are considering the variable length of the sequence, this is impossible to have one single feedword to apply to a variance length of the sequence. But still, I mean, you can use convolution to replace the dense linear layer. But that is one reason that the simple MLP does not work, because simple MLP works on the whole sequence. And even though if we can work on the whole sequence, it is so the network would be, I mean, you can have a MLP that can I mean, even for the transformer, it also has a context window, right? And because we have a positional encoding, so there will be some limitation on the length. So why not just use a huge MLP? The reason is that a huge MLP is just too huge. So the memory storage wise and the computational wise is too expensive. Also, that's another reason. If we wish to use MLP, we are going to apply to each vector. The reason that we're not using like convolution things is that because we are using transformer right here, so we don't need to. So the purpose of a convolution things, or maybe like a LCM things, is kind of complete or like overlapped with the multi-head attention. Also, that's why this one you can just simply view it as a nonlinear layer. Also, the transformer block of the encoder is quite easy, quite simple and straightforward. So there are certain modifications here and there, but it is just a simple contraction with the attention. About the outputs, we'll talk about it a little bit later. But basically, you can see that it is very similar to the encoder, except it also has a positional encoding, which is there will be you can use the same thing, and also the embedding you can use different thing or similar thing, depends on your application. But you can have a different embedding. But you can see that the first layer, first block, and the last one is exactly the same as the position. I mean, for the encoder, the only difference is it has. I mean, according to this illustration, there are some other subtle differences which we will talk about later in this lecture, or if we don't have it, we'll talk about next week. The only difference is, aside from the subtle difference or actually crucial difference that we would mention, is the middle block right here. It will has a multi-head attention, but it will have a cross attention to this guy. So this is also an attention layer, but this attention layer is used for taking additional information from the encoder. So this is the only way that the decoder extract or obtain or retrieve the information from the encoder. 所以你看到这个 decoder 跟 encoder 其实超像的，头跟尾几乎都一模一样，唯一不一样的地方是中间的。它有一个 很细致的地方不一样，特别是我们之后刚才讲到嘛，你ChatGPT只有 encoder，只有 decoder，所以中间这一层也不见了，那只剩下头跟尾，那不是完全一模一样吗？这个还是有不一样的地方，我们之后会讲。但你看这张图来说，它真正不一样的地方是中间这个地方，它这多了一块，这个地方是用来去取得 encoder 的资讯，不然的话你就自己跑就好了嘛，你就跟它输入完全无关了啊。但是它必须要从这边取得资讯，那取得资讯最容易的方法就是我用 cross attention， 这边单纯就是用 cross attention。好，等一下我们会讲 attention， 所以我们可能不会讲到说 encoder 跟 decoder 的差异性了那个地方，但是你可以知道这边是拿它的那个资讯进来的地方。Another difference is at the final part, it also has a linear and a softmax right here, and has an output probability. So this is the final differences right here. But the block itself is pretty much similar, especially if you consider the decoder only architecture, in which the middle part is not necessary because there's no encoder at all. And the middle part serves as a retrieve information from encoder. So if you don't have an encoder, the typical decoder design is to just discard or like eliminate this middle part. So it only consider the first part and the last part, which means it is exactly the same as what would look like as an encoder. But still there's a different. So for example, like a BERT is an encoder-based model. The BERT is different from GPT because GPT is a decoder-based model. But suppose it only has an encoder and one only has a decoder. And the middle part does not exist for a decoder. Why do we call the BERT is encoder and the ChatGPT is a decoder? There are still differences, but we'll talk a bit later. First, let's talk about what the attention block is. What the attention block is. Okay, so the attention block can be viewed as this thing. There are different kind of attention. The attention that we are using, the most popular attention is called the scale dot product attention. This is called the scale dot product attention. Can be either self-attention or cross attention. But this is called the scale dot product attention. So what is a scale dot product attention? Basically, the architecture of attention will consider three different input: query, key, and the value. Let me try the writing again because this is okay. Let's work. That is query, key, and the value. It sort of look kind of like your dictionary. Like you have a dictionary, like Python dictionary. So you have A, and the key is A, and the value is 1, and like B, you got 2, C is 3. So in Python terminology, this A is called the key. In the dictionary, it's called a key. And this 1 is called the value. So this is a key value dictionary. Sometimes we call it a mapping. Or maybe it has the relational storage or other things. But okay, this is common scenario. We have a key and a value pair. The purpose of this guy is when we make a query, like this one, like when we ask. So say this one is called D for dictionary. You can ask D A equals to what? So this one is a query. You can query to find out the the storage and the value over the corresponding key. So this is a simple key value storage. And when you give a query, it will get an answer. However, attention can be considered as a soft dictionary, which means your query may not be exactly the match of A, B, C, D. It could be something like 90% of A and 5% of B and 5% of C. So this is a query. Be something like this one. Okay, so the only difference of attention and the dictionary is your query is a soft query, and we'll find we will find your query and to find the similarity to each of the key. So for a dictionary, either it is 100% A, 100% B, 100% C, or it is not in a dictionary, right? So this is called a hard dictionary. Either it match or it is not, and it only match one thing. But for a soft query, this is a soft query or a soft dictionary. That's called a soft query. Is we are trying to find the similarity of this query to this key. So the typical scenario is that we'll have a probability things, like 90%, 5%, and 5%, things like that. But it will be a weight. It is not necessary to be a probability, but I mean, yeah, it is a scenario. It does not necessary to be a probability. It is not necessary to be a probability. But in this particular case, because we have a softmax, it is going to be a probability. But the idea is just like a query, but we query it softly. But in some case, you can use something instead of softmax. You can use something other than softmax. It still kind of work like a weighted query. You can query something like different. But right now for simplicity, because we are using softmax here, you can consider this as a probability. OK， 所以这个的我们就是一个软的 query， 所以每一个 query 我们会把它不会直接对应到每一个 key， 而是可能是说跟 A 有90%相似，5%相似，跟 B 50%相似 ，C 有50%相似。我们可能会用这种方式，而不是100% A 或者100% B 或者100% C， 或者都完全不中。它不管怎样就会一定会中，而且就是只是看多项而已，会分散在不同的地方。当然有可能极端的情况下是100-0-0了，但是一般来说它就不会，因为我们是 softmax 也不可能刚好100了，就是以数学上来说，它那个当然你有负无穷大的当然是另外一件事情，但是基本上就是一个几率了。OK， 好 ，OK， so after we get this similarity, OK, we understand this concept. We can have a soft query. What is the corresponding value? We simply do a weighted summation or weighted mean on the value. So in this case, because the value of K is 1, the value of B is 2, and the value of C is 3. So the output should be 90% times 1 plus 5% times 2 plus 5% times 3. So this is our final output query. So it would be something like 0.9 plus 0.1 plus 0.15. So in the end, it's going to be like 1.15. It's going to be something like this one. So that's all. So that's what the attention does. A single head attention does. Not restrict to scale product because we haven't talked about the mechanism behind. But this is something we wish to have, like a soft query. Of course, the value should be a vector. So you don't need to worry about the whether or not it can be do the weighted summation. It can, because we are working on vectors. If you want to generalize it, it still need to support the things like addition or multiplication. But basically, we are working on vectors, so we don't need to worry too much about it. This one works for vectors as well as numbers. But we still need to figure out how do we actually do the mechanism. But before that, what is the benefit of a soft query? The key is that we always will have an output, even though our query is not exactly match. We can still have an output. So that's one of the benefit. We can, and also it is sort of like a similarity test. We can still kind of mimic or simulate the mechanism that finding the relevance of one thing to another. Okay, so this one is a very useful contrasting tool. Imagine that when we do the n-gram, one of the drawback of the n-gram thing is if you encounter an unseen tuple, a tuple that is not exist in your trained data, you get no result. So suppose if you can have a result for every input, and if the input is in the dictionary, you can have the correct output. That's okay. But even if it is not in the if it is not exactly match, and suppose we can output something that is reasonable, then it will be pretty good. We probably mentioned that one way to do that is using a certain kind of neural network. So that's one solution. And this attention mechanism is even kind of arguably more straightforward approach, because you can define in a certain way that if it is exactly match, then it will be output the exact value of that key. And if it is not, then we still got some kind of output. And you can update the dictionary. It is more convenient, kind of like the counter dictionary that we have for the n-gram thing. This dictionary is kind of independent to the neural network itself. It can be updated and changed depending on your input or your context. So it is arguably a more straightforward and direct analogy to our like a dictionary, or like what we want to have for the n-gram, comparing to if we do it like a neural network directly, because we need to train. So it is more like a trainless neural network, depend on, or like a universal neural network they can apply to any kind of inputting data. 好，所以这个东西其实就有点像我们之前讲那个 n-gram。我们这 n-gram 不是一个像是一个 dictionary 吗？那个 dictionary 它的缺点就是，如果它是训练集合没看过东西，它就不会 output 东西出来，就死在那边，那个程序就死在那边。那所以我们说其中解法就是你用神经网络嘛，去训练来取代它。那这个东西就有点像，它是另外一种方法，而且它更直接。那它不用训练，因为它是已经训练好一个东西，那可以针对任何的资料。所以用法不一样。所以如果你是用神经网络取代之前那个 dictionary 的话，你要重新你拿到一个新的一个训练集，你要重新在上面跑一次训练。那每一次训练结果还有一些随机性。但这不是，这我们训练一个网络这个东西，或者一个演算法这个东西，然后你每次拿新的资料进来，就可以把这个算法放在上面，然后一样是要去找东西没有错，但是就可以达一样的效果，就是它是软的找东西，而且 假如刚好 match 的时候，它还是更好的是，它会得到一样的结果。Okay, so let me explain what the this scale dot product thing is. Okay, so okay, let's come to see right here. So we'll have a Q, which is a vector, P, which is also a vector, and V also is a vector. And the Q and the K will have same dimension. The scale dot product attention. The first keyword is dot product 就是点击或者称内积。So if we are consider a real vector space, the dot product is the inner product that you are familiar with. So the matrix multiplication is in fact the dot product. So we have like a Q1, Q2, Q3, and K1, K2, K3. So the reason that we would write it as a multiplication is we consider this one as a metric called Q, and this one consider a metric called K. So we can do a dot product of Q1, K1, Q1, K2, Q1, K3, and Q2, K1, Q2, K2, Q2, K3, Q3, K1, Q3, K2, Q3, K3. These all 9 different dot products using one operation called the Q TK. Depends on you are using column or row vectors. There'll be different notation. So in the paper, it using in the convention of this paper, it is using like QKT. So each of the K should be a row vector. Okay. So after KT, it becomes a column vector. And each of the Q in the Q is a row vector. So we'll have a different dot product. Okay, to simplify the explanation, let's consider just only one query. The case of one query and the 3 different key and values. So we do the Q1, K1 here to have a Q1, K1. So we have a Q1 dot K1, Q2 dot K2, and Q3 dot K3. We have 3 different values. Q1 dot K1, Q1 dot K2, Q1 dot K3. So we have 3 different values. So Q1 dot, let's just call it Q. K1, Q dot K2, Q dot K3. This is kind of like a cosine similarity, but we're not trying to normalize it. Instead, we're just using the inner product, the dot product value as is. Let's first skip the scale and the mask. So after we get this dot product, we are using it more like a cosine similarity, since in the sense that the higher value is more similar. So if it is a large value like 100, 1000, then we consider it more similar than like 10, 1, or -1, or -100. So higher the value, higher the dot product, we'll consider it more similar. But it is not a probability. So we're using softmax to map these values into probabilities. Okay, so we'll get attention map called this is called A1. After the softmax, softmax, we got attention weight A1, A2, A3. These are the similarity weight of each value, and the summation of A1 and to A3 is 1. And A1, A2, A3 are all positive, at least non-negative real numbers. So the output would be like A1 times V1 plus A2 times V2 plus A3 times V3. So this will be the output. Since we will only decide one query, suppose we have like 3 queries, then for each queries we'll have a corresponding output. So we'll get a new sequence of vectors. And the dimension of the output sequence will be the dimension of V, because K and Q are only used for determining the similarity between the position of each of the things. So in the most usable case right here, the output sequence will have the same length of the query sequence. The query is a sequence of vector, and the K1, K2, K3, and the V1, V2, V3 are pair of vectors. And they also have, if we are using a self-attention, they also have the same length of as the Q, as the input sequence. But if you are considering cross-attention, they are not necessary to be related. For the output dimension, the vector dimension of each output, the length is the same as the query length, but the dimension of each vector is the same as the vector of V right here. Okay, so that's the basic idea of what a dot product attention is. The only thing is that we are not mentioning about the scale. So let's look at the formula of the things. If we are ignoring this guy, QKT is simply the dot product of the query and the thing, and the softmax works for each row. It works for each row, and when we got each row, we do a multiplication right here, and we get the result at here. Because this multiply, we should get for each, we get it for each row. So for each row, we get one value. Okay, so by simply ignore this guy, this is exactly what we have already done for the attention described above. So the scale part, the scale dot product, the scale part is this guy. Okay, so what is the scale has to do? 好，所以我这边只要说这个前面这种，假如你先不看上面这个除以根号 dk 的话，这个 QKT 和 V 就是我刚才讲的，只是我刚才想把它只是把它变成一个式子而已，就完全是我刚才讲的东西了。好，但是为什么我这边只是要说的事情就是这个东西看起来有点复杂，但是其实跟我刚才讲的其实就是同一件事情而已，只是他写成数学式子，然后就看懂就是那个式子而已。但为什么会有下面的根号 dk? So why would the only question left? There are 2 questions left, which we will answer next time. It's a mask, but we are going to answer why there is a scale right here. Why is there a scale right here? The scale is because we are using a softmax, and softmax is very sensitive to the input things. Because if you remember what the softmax is something like EA1 plus EA2 plus EA3. If we want to consider first component, this is like EA1. For the second, the probability of the second one is EA2. So there's an exponential right here. And what is A1, A2, A3? A1, A2, A3 is the dot product of like Q. I should not use A1, A2, A3. I should use that like it is something like logic. So I'm using L right here, like the L1, L2, and L3. Logics right here. And L1, L2, L3 is in fact Q.K1, Q.K2, and Q.K3. This is 3. If the Q dimension of Q is really large, not that the dimension of Q and dimension of K is the same, which is like a dk right here. You can see a dk. dk is the dimension of the key and the query. The dimension of the value is dv, which may be the different number. If a dk is really large, like 1000, this dot product is going to be really large, right? 好，所以你的 dimension 如果很长的话，1000的话它相乘，然后它就会就很大嘛。如果是10000的话，就会更大。So basically, if we consider each of the element as a random variable, independent random variable, which may not be a exactly correct assumption, but this is probably the best we can get, and we probably want it to be sort of independent to make the representation more efficiently. So we can sort of assume they are independent random variables. So how large would it be? Recall that the expected value of a summation of random variables doesn't need necessarily to be independent. It's in fact the summation of expected value of this guy, random variable xi right here. So suppose each element has the same random distribution, and assume they are independent. It is going to be rather large. Consider this guy. Okay, so which means that if it is when the dimension is getting large, this guy is going to be rather large, and because we are going to the exponential, sometimes it is going to be too large if the dimension is too huge. So we need to sort of compensate the effect. Otherwise, the behavior would be very different, and sometimes it will going to be very difficult to train. 所以那个数字如果太大，这 L1、L2、L3，它尺度如果太大，这个东西会变得超大，甚至会爆掉，而且不好训练。然后我们也不容易去控制它，我们需要它so we need to sort of normalize it. Okay. So first you ignore what the square root is. By the intuition above, you probably will know that if the if this guy is going to be larger, this guy is going to be larger, then we are going to have make it smaller. So that's what the scale is. So if dk is larger, we divide by something like this one, it will make it smaller. So it is toward the right direction. Okay, but why we use the square root of dk? Not just dk or other like dk square or things. The reason is that if we assume them qk, I mean, each of the element is a random variable. When we try to normalize it, assuming their expected value is going to be 0, which is a stretch, but that is our assumption. It's a very common assumption. Suppose them to be have a 0 mean. So how do we normalize it? We will normalize it by the standard deviation, right? By the standard deviation. we usually normalize things by divide it by standard deviation. Okay, so how does the standard deviation related to our dimension? The standard deviation is corresponded to, suppose we have n we have a random variable like this one, like xi. Suppose each of xi, the standard deviation. Let me write like this one. They have their mean is 0. Suppose their variation is sigma square. Then the summation of n of them is going to be n sigma square. This is because the expected value is kind of linear, so it can this guy and this guy can be exchanged. 好，所以这其实从那个基本的那个期望值，你可以知道期望值是可以相加的。所以假设它们的命都是0，那这个东西其实就是它的variance 嘛 ，sigma 平方 ，sigma 是它的那个每一个个别的 standard deviation， 然后它的平方就是它的那个 variance。那 variance 本身如果它们本身是没有 correlation 的话，这可以相加的。好，所以这 n 个就是 n 个。这边如果有 n 个的话，就是 dk 啦 ，n is equal to dk in our case, and xi is probably some like a qi, ki. This ki are like kij, qj, kij, something like this. Okay, so you can see that the variance, if the dimension is n, the variance is going to be n times the variance of one element. But we usually kind of like divide to normalize, we should divide to its standard deviation. So the standard deviation of this guy is the square root of this guy. So which is like square root of n of sigma. So that's why we will have a square root of n right here. Because in this case, the n is dk. Also, that's all. That's why we have this. 好，所以这边就是我们讲到的地方。那 so next time we are going to talk about what the mask is. This is the difference between the encoder and the decoder. Otherwise, we are already talking about what the cell dot attention is, and also we are talking about what the multi-head attention is. 好，那我们今天就上到这个地方，那下次会继续介绍scaled up attention 和 multi-head attention，还有这个 mask。这个 mask 就是 encoder 跟 decoder 的差别。